Required derivation number 4 is all about the moment of inertia. Consider the simple rotating system shown in the picture. Assume the masses are attached to the rotation axis by massless, rigid rods. The kinetic energy of this system will just simply be the sum of the kinetic energy of all of the pieces here, all of the masses. And the kinetic energy is equal to 1/2 mv squared for each one. So if we wanted to know what the rotational kinetic energy of the entire system was, then we would simply add up the kinetic energy of each of the constituent masses. However, you'll notice that the masses are at different distances from the center of mass about which the system is rotating with omega. And so M1, which is the furthest away, has to be moving further than M2, which looks like it's the closest. If we were to recognize the relationship between V and omega, then we could substitute in for V initial, or excuse me, for VI for each of the masses, omega times RI. When you do the algebra, what you end up with is 1/2 omega squared times the sum of MI RI squared. This quantity here needs to look sort of like a mass quantity if we are to have a kinetic energy that looks like 1/2 mv squared. And so we call the sum of MI RI squared for all of the i's, all of the masses, the rotational inertia or the moment of inertia about the rotation axis. Notice that the units will be mass units times position units squared, or kilograms times meters squared. So we identify the kinetic energy of the rotating system as 1/2 I omega squared, where I happens to be the sum of all the MI RI squareds. Notice that the moment of inertia I depends on the distribution of the mass, not just how much mass you have. The further the mass is from the rotational axis, the bigger the moment of inertia. For a given object, the moment of inertia will depend on where we choose the rotation axis, unlike the center of mass. We will see that in rotational dynamics, the moment of inertia, I, appears in the same way that mass does when we study linear dynamics. It's completely analogous. Finally, for a discrete collection of point masses, we can calculate the rotational or moment of inertia, I. But if we are working with solid objects, which would be a continuous distribution of point masses, then we have to add up the MR squareds for every infinitesimal piece element dm. And so our summation becomes an integral, and we calculate I for different extended masses as the integral of r squared dm. This slide will contain the derivations of the calculation of I for absolute required object systems. Our first example has a stick that's rotating about an axis on its edge. What we need to do is select a representative differential piece of mass of length dm or dl and mass dm, and then we have to calculate the rotational inertia of the entire stick by integrating for each of these differential masses the integral of r squared dm. We're going to integrate from 0 to L and use the variable x in place of r. Now this is an integral over mass, and we need the integral over position. And so what we do in these situations is we identify a linear mass density, which is mass per length. Of course, this linear mass density, lambda, is also equal to dm over dl. And so we can solve that relationship for dm and express it as lambda dl, or in the integral lambda dx. So once we have this integral set up, we follow through with the integration steps, and we end up with I of the stick about an edge. Our second example is rotating the same stick, not about an edge, but a middle. I see I have a typo there. That should be an L in middle. In any event, We do the same thing. We select a representative differential piece of mass of length dl or dx, and we start with our integral of r squared dm. And in this case, the limits of integration, when we add up all of those pieces, go from minus L over 2 to L over 2. We carry out the integration and get the result. The third example is finding the moment of inertia of a hoop of mass m and radius r, rotating about its center of mass. We again select a differential piece of mass, dm, and we follow through by sticking it in our integral. But all the mass elements, dm, reside at the same distance from the axis of rotation, so r is constant and we can pull it out front, leaving the integral of dm, which is just the total mass, and thus yields I is equal to mr squared for a hoop. The final required derivation for moments of inertia is the calculation of the rotational inertia of a circular disk of mass m and radius r. Again, our starting point to calculate the rotational inertia is the integral of r squared dm, but we have to determine what our dm is. And in order for us to evaluate the mass and add up all of those differential dm's, we have to define our dm as having a circumference of 2 pi r and thickness dr. So now we have a differential area associated with this dm, which we can then integrate. And so using the same trick as before, but instead of using a linear mass density, we use a area mass density. Sigma is now defined as the mass per area, and of course the area is pi r squared. So sigma could also be represented as dm over dA, which then can allow us to use the algebra to get dm is equal to sigma dA, where dA is defined as 2 pi r dr. So now we have an expression for dm which we can substitute into our integral, pull out all our constants, and evaluate the integral, and this is the result of the moment of inertia of a circular disk. I have put two more examples for finding the moment of inertia of an extended mass. One, the top one on this third slide, is a hollow cylinder of mass m with inside radius a and outside radius b. I'm not going to go through the details of this derivation, but you can see we start with the same I equals r squared dm, and we have to develop an expression for dm. The last example on this slide is the thin rectangular plate. Again, to calculate the moment of inertia, we find the integral of r squared dm and find an expression for dm to get the answer.